August 6th, 1945 is a day of infamy in world history. In what must have been one of the most difficult decisions in the history of humanity, U.S. President Harry Truman ordered the release of a single bomb over the Japanese city of Hiroshima, containing just 64 kilograms of ordnance. That's about 140 pounds, far less matter than there is in the man standing before you right now. Now, if that ordnance were a conventional explosive like TNT, that would not have even been enough to make the nightly news broadcast on that day in world history. But this ordnance was special. It was decidedly unconventional. This payload detonated 1,900 feet above the city, just as planned, releasing a blast that leveled an area 1 mile across, releasing the amount of energy in an explosion of 15 kilotons of TNT. This is more than 200,000 times the explosive yield per pound versus TNT. To put it another way, if you had a pile of TNT equal in mass to all the steel in the Eiffel Tower, you would have a bomb half as powerful as that 140-pound device. This device was able to release such a blast because it was not releasing chemical bond energy. It was releasing nuclear binding energy, which we've already learned can be tremendous by comparison. Of course, by now you must know that I'm talking about what might be the darkest day in the history of war, the dropping of the first nuclear bomb on Japan, an act which almost certainly precipitated an end to the conflict, but at the cost of many, many lives. We've discussed this weapon before when we saw the tremendous lengths that scientists and engineers of the Manhattan Project went through to obtain isotopically pure uranium-235. Remember, they used a fusion of uranium hexafluoride, exploiting Graham's law. Now, by the end of today's lecture, we're going to better understand exactly why that effort was so necessary. So far, we've confined our discussion on radioactivity to the emission of relatively small particles from relatively large nuclei. Most prominent in the discussion were beta particles, which are high-energy electrons, and alpha particles, which are helium nuclei. But the thought must have crossed your mind at some point. Can something larger than an alpha particle be lost from a nucleus as large as uranium? After all, if iron-56 is the goal, large atoms like uranium could get there much faster by shedding much larger fragments of other, more stable nuclei, right? Right. Although alpha, beta, and gamma radiation are all by far the most common decay processes that elements like uranium take to try to reach those more stable states, they are not the only ones, not by a long shot, especially when the nucleus is a little bit less stable than normal. Enter a new isotope into the discussion, uranium-235. Uranium-235 makes up a very small percentage of naturally occurring uranium, less than 1%. But it has something that uranium-238 does not, the ability to break into two nuclei of nearly equal size. When nuclei can break into two pieces, both larger than an alpha particle, we call them fissile, which means breakable. And one of the reactions that uranium-235 can undergo spontaneously is this fission reaction, in which uranium-235 breaks apart into two larger nuclei, a barium-141, a krypton-92, and in order to maintain that mass balance, we have to remember that two neutrons are going to result from this process. So let's watch that happen here. I've got my uranium nucleus. It's going to break, and in doing so, create the two neutrons that we would call radiation, right? But we would also have to admit this is a fission reaction because we created a relatively large daughter product here in krypton, and we've also, of course, got the barium. So the fact that two large nuclei resulted, much larger than any alpha particle, we would call this a fission reaction. Now, specifically, we'd call this one a spontaneous fission reaction because the U-235 nucleus will do this all on its own without any kind of perturbation. Slowly, yes, over very long periods of time, but it will happen just spontaneously. Now, what you just witnessed was one of the primary ways, but only one of many ways, that uranium-235 can break apart into two smaller nuclei. In truth, when uranium-235 breaks down, it produces a series of nuclear reactions, all of which release energy and produce new elements. I want you to keep that in mind. But for now, let's focus on just the dominant primary reaction taking place. The fission reaction of uranium-235 and the energy that it releases makes it a remarkably useful atom. Part of what makes this and other fissile nuclei so different from those like uranium-238 that only undergo simple, steady radioactive decay is that fissile nuclei can often be made to undergo fission either very rapidly or very slowly. I'm waiting for that hand to go up. Remember radioactivity? Last time and during our rate lectures, we discussed how the radioactive decay of elements was a first-order process and occurred at a fixed rate that could never change. It's so predictable and unchanging that radioactive decay is the basis for radiological dating methods. And now here I am telling you that the fission of 235 can be made to happen slowly, enough to support power for electrical needs for years, or to be over in less than a millionth of a second, causing an explosion the likes of which humanity has never seen. So am I lying? Of course not. I left out one critical factor in the fission of uranium-235. This detail was worked out by Enrico Fermi, a physicist working on the Manhattan Project in the early 1940s. See, Fermi had studied the fission of uranium-235 in great detail at the University of Chicago and was convinced that he was onto something. Fermi discovered that unlike radioactive decay, which relies simply on the statistical likelihood that a nucleus will spontaneously eject an alpha, beta, or gamma particle in a given amount of time, nuclear fission of uranium can be induced by the collision of a neutron with the uranium-235 nucleus. And here's the kicker. Remember that the reaction itself also produced two neutrons. Since we've already established that a neutron can be generated in the spontaneous fission of uranium-235, it seems like it would be wise for us to consider what happens when that neutron collides with yet another nucleus of uranium-235. And we would call this a collision-induced nuclear fission. In this reaction, notice that I now have a neutron over here as one of my reagents. So the neutron is going to come from outside, collide with that U-235 nucleus, and in doing so, it's going to initiate another fission, just like we saw previously. So our neutron collides, creates those fission byproducts, but it also creates two new neutrons and the original neutron. So now I'm creating 3 neutrons for every collision. And of course, these neutrons potentially could move on and induce additional fission reactions to take place in other U-235 nuclei, if they're present. Which brings me to this, what's known as a nuclear chain reaction. Now, I've set up a few U-235 nuclei here so that we can watch just the first few steps of a nuclear chain reaction, the likes of which might be going on inside of a nuclear reactor, or one of the relatively simple nuclear bombs that were developed by Teller in the Manhattan Project. It all starts when one of those U-235 nuclei undergoes a spontaneous fission. So over here, I've got my lone U-235. This one's going to kick off my reaction. When it does, as long as I have an adequate density of uranium-235 nuclei around it, I can expect the neutrons it generates to kick off more fission reactions, which should kick off even more. And what happens is if I have enough U-235 handy, I get a chain reaction in which one fission begets more fissions, which begets even more fissions. And you can see very quickly I can build up a relatively large population of neutrons flying around inside of that sample, colliding with new uranium-235 nuclei and promoting more and more of these reactions to take place. This is the nuclear chain reaction. So the 2 neutrons formed in a spontaneous fission can go on to impact other uranium-235 nuclei and perpetuate a chain reaction by induced fission. So the concentration of neutrons flying around in a sample containing uranium-235 directly affects how rapidly the sample will undergo fission. Physicists call this concentration of free neutrons in a sample of material neutron flux. And you know what all of this means. Because fission of U-235 is a second-order process overall, the fission of U-235 can be accelerated or decelerated simply by controlling the neutron flux. We've reached a point now where we can get a bit more detailed understanding of why it is the scientists at Oak Ridge National Labs were so intent on enriching their uranium samples. Remember, we talked about this many lectures ago, and how they use the process of gas effusion to get more uranium-235 isotopes in their uranium samples. Now, to demonstrate why that was so important to their goals, I've created a little mock uranium sample here, if you will. Now, this is a really popular demonstration. You may have seen it done before, but we're going to analyze it very carefully in terms of neutron flux and try to understand why we have to get extra uranium-235 in our samples to make these kinds of devices like nuclear power plants and nuclear bombs function. In this case, I have mouse traps set. And most of them actually are not set. They're simply placed on the table. And these would represent uranium-238 isotopes. Those isotopes do not undergo nuclear fission very easily, if at all. That's why the traps, of course, aren't set. But you will notice that I have just a few traps that are set. And on top of them, I placed a ping pong ball. Now, those traps represent uranium-235 nuclei. And the ping pong balls represent those neutrons that are released when they do undergo fission, right? We call this a fissile isotope. So at the moment, I have a very, very low population of fissile isotopes. In fact, just about 5% of my traps are set. Now, uranium-235 itself is only about 1% abundant in natural uranium. So this is actually an exaggeration of how many fissile isotopes we would see. But even so, when I set off one of my traps using one of my free neutrons here, so let's say a free neutron is going to go through my sample and strike one of my fissile isotopes. Now, when this happens, if the neutron flux is sufficient, I should be able to set off all of my uranium-235 isotopes, eventually causing them all to undergo fission. So let's see if I'm successful using my natural abundance analog here. So I'll put some protection on just in case things work better than I expect them to at this point. And I'll take my one neutron that I'm going to use to induce fission in one of my nuclei, and we'll see if we can accomplish a chain reaction in which the neutron formed in that fission event then goes on and creates a second fission event, and so on and so forth. So here we go. Incoming neutron. What happened there? Well, I did manage to release one neutron through fission, but that neutron didn't have a very target-rich environment. There were very, very few other fissile nuclei present. As a result, the chain reaction stopped. It never really got started. So, keeping this in mind, let's reset and make one little change here. Let's increase the population of our fissile uranium-235 isotopes and run this experiment one more time. Well, as you can see, I've reset my experiment here, and I'm using all the same cast of characters that I did previously. I have my unset mouse traps representing uranium-238, and I have my set mouse traps representing uranium-235 nuclei, and of course my ping pong balls as the neutrons. But I'm sure you notice one very striking difference, and that is that now I've got about a third of my traps set. Now, this would be my representation of what we call fuel grade uranium, which is enriched normally to about 4 to 5% U-235, but to get the same effect here, I've had to go a little bit higher with my mouse traps. However, I've increased the concentration of the fissile isotopes in my sample. And what we're going to do now is exactly the same thing we did last time. I'm going to introduce that one stray neutron into the system, and we're going to observe the neutron flux and see if it's any more effective than it was last time. Of course, in the case of nuclear power, the goal is to achieve a long, sustained reaction in which the energy released from the fission of these isotopes can be tapped over long periods of time and ultimately, of course, converted into electricity for our power use. So let's see if we can accomplish that using the somewhat enriched uranium-235, our set mouse traps here in this example. So I have my eye protection back on again. Again, my one neutron that I'm going to use to try to initiate a chain reaction, and this time my enriched uranium sample, and we'll see if the neutron flux is adequate. Okay, you ready? Here we go. Well, we saw something a little bit different there, didn't we? Right? The same type of process was going on, but there was a longer, more sustained reaction that went on there where the neutron flux continued because we had more neutrons to be released from our more fissile nuclei, and of course we had a more target-rich environment because about a third of our traps actually were set. So that's the type of nuclear reaction that one wants in a fuel source. If we were going to use this to generate long, sustained energy, this would be a perfect reaction to do so. So by enriching the uranium somewhat, and using other techniques like the insertion of control rods to slightly decelerate the reaction if it does get out of hand, nuclear engineers can create these kinds of reactors that will deliver long, sustained, safe nuclear power. But there's one more use for these types of substances that we want to discuss, and that is nuclear weapons. Now, in order to do that, we're going to have to enrich our sample even more. I'll be right back to show you what happens when we got nothing but uranium-235 on the table. Well, we're back, and as you can see, we've reset our demonstration one more time, but with another change. We have increased the concentration of uranium-235 yet again. In fact, every single mousetrap on the table is now set with a ping pong ball on top. So this would correspond in our analogy to 100% pure uranium-235, the fissile isotope. Now, weapons-grade uranium is actually almost that pure. It's about 90 to 95% pure, so we've just gone ahead and decided to load every single trap. And what I'm going to do is exactly the same thing I've done previously. We're going to introduce a neutron to begin what we hope will be a chain reaction, and we want to pay close attention to the neutron flux, right? Because in this case, for an explosion, we want a massive release of energy. We want that chain reaction to run away. Okay, here we go. I'm going to get my eye protection on one more time, and I'll introduce my neutron, and we'll observe the neutron flux that we get with our highly, highly enriched sample of uranium-235. Here we go. Well, we saw something a little bit different yet again, didn't we? This time, instead of a slow, sustained neutron flux, the neutron flux absolutely ran out of control because there were so many available fissile nuclei, so many targets, so many neutrons moving around in there, that all of the energy was released in a very, very rapid reaction. This is the kind of chain reaction that you want when you're designing a nuclear bomb, and this is why weapons-grade uranium has to be so very, very highly enriched in uranium-235. So our fissile nuclei, loaded mousetraps, break only when a neutron, ping pong ball, hits them. Now, ping pong balls can be coaxed to release their energy more slowly if we can keep the number of triggering projectiles, right, those neutron/ping pong balls, down to a minimum. Or we can also space out the reactive nuclei so that they're farther away from one another. Fermi was confident that he had this all worked out. So confident, in fact, that when his plans to build the world's first working nuclear reactor in an isolated area of Illinois fell through, he decided instead to go through with his demonstration by building it underneath the University of Chicago. Fermi piled uranium and graphite in a large, spherical-shaped arrangement, not within tons of concrete, not cordoned off by barriers of lead, but right out in the open in a tennis court under the west viewing stands of the abandoned Stagg Field at the University of Chicago. At 3:25 p.m. on the afternoon of December 2nd, 1942, Fermi's pile went critical and began producing his chain reaction, which was sustained for 28 minutes. He'd proven his point. He had risked countless lives, including his own, in the process, but he'd proven his point. A sustainable chain reaction could be created and controlled. Inside a nuclear reactor, the neutron count is kept down using rods made of a neutron-absorbing material, such as indium or cadmium. Rods of this sort of material can be lowered into the nuclear fuel to decrease available neutrons or raised to allow more neutrons to continue in the reaction. Using this technique to control neutron flux and a fuel made from uranium as it's recovered from ore, meaning just about 0.7% U-235, we can sustain a controlled nuclear fission reaction for about 6 years with just a little bit of human help. Nuclear reactors were a brilliant invention. They use low concentrations of uranium-235, so they can't create a nuclear explosion, even under the worst imaginable conditions. But they're not without risk. Most nuclear power plants are actually sophisticated steam generators. A reactor core containing nuclear fuel is used to generate heat. The heat is often then used to generate steam, which turns turbines to create electricity. Because the U-235 abundance in the fuel is so low, a nuclear explosion would be absolutely impossible. But the temperatures that can be generated by a runaway reactor are so high that a host of other catastrophes can happen when things get out of hand. One of the more famous examples of this is the 3 Mile Island incident, which happened on March 28, 1979 in Pennsylvania in the United States. During this incident, a valve intended to release steam from the water cooling system stuck open, allowing most of the water coolant to escape from around the reactor. As the core temperature rose, operators tried to lower control rods into the fuel to slow the reaction by absorbing neutrons, which would reduce the neutron flux. But it was too late. The heat from the runaway reaction had so badly warped the core that the control rods wouldn't even fit into their receivers properly. The reactor was doomed. As the temperature inside soared, the reactor itself melted into a puddle of nuclear material at the bottom of the core. This was dangerously close to becoming a case of what reactor engineers call China syndrome, in which the molten reactor material melts through the floor of the core and deep into the earth below, on its way to China, as it were. Fortunately, the core walls themselves withstood the stratospheric temperatures, and no nuclear material escaped from 3 Mile Island. This is in contrast to the infamous Chernobyl accident, in which the plant operators and the people of Chernobyl in Ukraine were not so lucky. A steam explosion there contributed to a reactor breach at this plant in 1986, throwing fuel and its radioactive byproducts into the air and the surrounding area. This scarred the town to the point of uninhabitability even to this day. Fermi's experiment under the University of Chicago in 1942 heralded a new age for humanity. He had demonstrated that man could control the nuclear fission reaction and harness it as an engineering tool. In the case of Fermi's pile, that goal was to create a self-sustaining nuclear reaction that could deliver continuous energy over long periods of time. And it did so, providing an early blueprint not just for 3 Mile Island and Chernobyl, but for many dozens of nuclear plants that have performed safely over the decades since they were designed and built. But this was all just a byproduct of the true goal. Fermi's work was funded by the famous Manhattan Project, an effort by the United States government to harness the power of nuclear fission for a very different application. Remember that Fermi's design was intended to run slowly. He used a natural abundance uranium sample in which U-235 atoms were diluted by their much more stable uranium-238 siblings. And he also used neutron-absorbing graphite to slow down the chain reaction in those uranium-235 atoms, sustained when neutron byproducts of their fission strike another 235 atom, perpetuating the process. Now, in our last demonstration, we controlled the rate of the fission reaction by spacing out our mousetraps and removing the byproducts of the reaction, just as Fermi did. But the real goal on everyone's mind was not to create a sustained fission reaction, but a violent one. Fermi's design allowed scientists to study the nuclear fission reaction closely and relatively safely. But research on nuclear fission continued. It was wartime, and the ultimate goal of the Manhattan Project was to create a weapon that could dispense all of that nuclear binding energy in an instant. The first nuclear weapons developed by mankind all relied on the nuclear fission reaction to work. They're based on the same principles as Fermi's stack, but with a few design changes to make the chain reaction deliberately run away as fast as possible. The two most infamous nuclear weapons in history, of course, the only two ever actually used in war, were products of the Manhattan Project: Little Boy and Fat Man. Little Boy used the exact same reaction as Fermi's reactor at Chicago. But in order to get the reaction to run away, there needed to be much, much more neutron flux than in Fermi's reactor. So instead of using control rods to reduce the density of fission-inducing neutrons, the facility at Oak Ridge National Laboratory in Tennessee spent huge quantities of time and energy to enrich uranium-235 beyond its natural abundance of about 0.7%, all the way to about 80%. This 100-fold increase in abundance ensured that there would be plenty of neutrons rattling around in that bomb's payload, making the sample potentially explosive. The next thing that was needed to produce a nuclear explosion was what is known as a critical mass of the fissile material. In the case of U-235 used in Little Boy, this mass was about equal to the weight of an ordinary human being. When the size of the nuclear material meets or exceeds critical mass, the neutron flux in the center of that mass is sufficient to start a runaway chain reaction that releases the nuclear binding energy in an instant, creating the massive explosions and accompanying mushroom clouds that we're all accustomed to seeing in historical films and photographs. Little Boy accomplished this using what is commonly called a gun-type design. In this design, two subcritical masses of weapons-grade nuclear material are kept separate within the shell of the bomb. One or both of those subcritical masses are then accelerated into one another by a conventional explosive blast. This is the origin of the gun-type name for the bomb. Little Boy's design made this device very slender and long, leading to the inspiration for its code name. So what about Fat Man? Fat Man was a different kind of device, one known as an implosion device. Fat Man consisted of a spherically shaped group of explosive charges designed to crush a plutonium core to increase its density. And this sudden increase in density decreases the core's critical mass to one below its actual mass. Add to that an extra source of neutrons at the very center of the core, and a nuclear explosion is almost guaranteed to result. The spherical design of the implosion device created a shell that was distinctly round in comparison to Little Boy, which earned this bomb its moniker, Fat Man. Fat Man was deployed to the shipbuilding port city of Nagasaki 3 days after Little Boy was detonated, and it caused similar devastation. It was the second use of such a weapon in combat. Thankfully, in the 70 years since, an explosion of such a magnitude has never been used in a wartime theater. So let's sum up our discussion. In this lecture, we discussed one of the most influential moments in world history, the use of the atomic bomb. We thought a little bit about the payload of the infamous nuclear weapon Little Boy, and the fact that it could deliver the explosive force of a pile of TNT 200,000 times its size. We considered the process of nuclear fission, in which heavier elements like uranium-235 spontaneously break into two or more smaller nuclei, pushing a system towards the optimal per nucleon binding energy of iron-56 and releasing enormous amounts of energy in the process. We also considered nuclear chain reactions and how the byproducts of nuclear fission processes, like neutrons in our uranium example, can go on to initiate other fission events. Now, we saw how the fission chain reaction can be used with graphite control rods and cooling water jackets to produce reliable power from uranium taken from the Earth. Then, we recounted two dark days in the history of nuclear power. The days when 3 Mile Island and Chernobyl power plants experienced reactor meltdowns with starkly different consequences. Finally, we took a look at how nuclear fission was used to create the single most destructive weapons ever deployed into the battlefield by our species: the gun-type fission bomb known as Little Boy, and the implosion-type fission bomb, Fat Man. We've spent some time thinking about the forces driving the breaking down of atomic nuclei as they quest to become iron-56. But we still haven't fully investigated the alternate scenario. What happens when two smaller nuclei aspire to become a larger one in the same quest? Now, we'll answer that question next time when we discuss nuclear fusion.